Hello, everyone. This is Haohuan from the Department of Earth System Science in Tsinghua and also from the National Supercomputing Center in Wuxi. It's my great pleasure to participate in this ISC workshop on machine learning hardware. And my topic today is about highly scalable machine learning methods on Sunway TaihuLight. So as you can see, I'm working in the Department of Earth System Science in Tsinghua University. And the Earth is, of course, one of the research focus of my colleagues at Tsinghua. For me, as I'm working also on the supercomputer, so one of the key goals that we are trying to achieve is actually to create a digital Earth so that we can use it as an important tool to simulate different kinds of climate change phenomenon on the Earth. And also we use the supercomputer to analyze the huge volumes of both observation data and simulation data. And by doing so, of course, the goal is trying to improve our understanding about the underlying climate change mechanism so that we could make better predictions into the future, and that we could also help the people to better mitigate the future climate change effects, especially those extreme weather or climate events. So along the process, two of the major functions we are trying to provide with the supercomputers. One is to provide simulation tools. So especially for earth science, you can't do experiments in the lab. You have to use the numerical models on the supercomputers to verify the different kinds of series that you propose. The second important function is, of course, to provide tools for data analysis, especially for those huge volumes of climate data sets. You need some highly efficient and also intelligent tools to find out the important information in those huge volumes of data sets. So our work as developers for the Sunway TaihuLight supercomputer. So one is to design highly efficient and highly scalable simulation applications. And the second one is to develop intelligent data mining methods for the analysis of big scientific data. Of course, the focus of this talk is the second part, but let me just give you a very simple example for the first part. So this is some simulation datasets we have generated for high resolution climate modeling on Sunway TaihuLight. So we have collaborated with scientists from Qingdao and also scientists from NCAR in US and to enable this high resolution CES and the community air system model on Sunway TaihuLight. And we have used it to generate, I think, the first high resolution datasets that cover over 700 years, 25 kilometers for the atmosphere and 10 kilometers for the ocean. So you can see using the simulation tools, we are already generating some very detailed and important information for the climate scientists to look at. Now, what we can do for the second part, what we can try to extract from those huge volumes of climate data sets. So here I just show you a figure. This is actually a figure that integrates a lot of research efforts for my colleagues at Tsinghua University. So these are different things that people try to do using the remote sensing datasets, which is actually a very important part of the climate change datasets. The data sets that people collected from the satellites is approximately half of the entire climate change data sets that people use regularly. Now, by looking at these satellite images, obviously you can do a lot of things. So let's start from the left corner. The land cover mapping, this is actually very important. So basically you get the satellite images and you use the machine learning algorithms to do the classification of the land cover automatically. So basically, the program will look at the image, the spectral information and all these different information that you can achieve from the satellites, and trying to tell you whether this piece of land is a forest, a grassland, a cropland, or a human building, or a desert, or a lake, and so on. So by doing so, this is actually generating a global land cover map, which is a very important basic data sets that you can use in many other different kinds of research. The second example we show here is the ecology protection zone. The goal of setting the ecology protection zone is, of course, trying to maintain the ecology diversity of that specific zone. And obviously, by looking at the satellite images, you can tell, in a decade or in a couple of years, whether the ecology diversity is maintained or reduced or even becoming better. And yeah, I have also listed other examples here. You can use these new methods trying to figure out the migration paths of the birds and trying to look at the cities, the greenland, and of course, the most important resources for human, the water, how the water bodies are changing over the years, and the sea level, the coastlines. All these different things, you can look at the satellite image and trying to infer this information using different kinds of machine learning algorithms. And if we talk about the resolution, so these images, the traditional Earth resource satellites like the Landsat, the resolution is somewhere around 30 meters. And if you are looking at some high resolution satellites, is already within 1 meter. And if you're looking at those UAVs, it can be even higher resolution. So these things are collecting really a rich set of information. If you look at those climate models, they're running at the scale of kilometers. So I think obviously there are some potential here to extract some better description of the change phenomenon on the Earth and trying to provide some complement to the current climate models. So this is the three major parts I'm going to cover in this talk today. So first, I'm still going to talk a little bit about the hardware, the Sunway TaihuLight hardware, which is, of course, the basic platform for us to do both simulation work and machine learning work. So Sunway TaihuLight, I think you guys should be very familiar with the machine by now. It used to be the top one system for the year of 2016 and 2017. Was the first system in the world with a peak performance over 100 petaflops. And it has a very high level of parallelism of over 10 million cores that you can use for one application. If you look at the processor itself, each processor has 260 cores, which is divided into 4 core groups. Each core group has one MPE, is a management processing element, and like the traditional CPU core can do both computing and management work. And then we have this 8x8 CPE mesh is the main computing engine that we use. So at the time that Sunway TaihuLight was built, deep learning was not yet a very important factor to be considered. But for now, for the coming exascale systems, the deep learning performance is already decided as an important benchmark metric. So we are expecting the next generation of Sunway supercomputers will be even more efficient for dealing with those deep learning or other machine learning type of algorithms. Okay, so the second part, the AI software, I will talk briefly about the efforts we have done in the last 4 or 5 years trying to make AI algorithms more efficient on the Sunway TaihuLight supercomputer. we actually did a lot of work, but here I'm just going to give you two examples. One is for the deep learning, the Sunway DNN library and the Sunway Cafe framework. And the second example is K-means. That is about how we could actually scale this kind of clustering algorithms to over millions of cores on Sunway TaihuLight. Okay, so first, the deep learning software stack. As Sunway is taking a completely different processor architecture from other supercomputers, even compared with its previous generation Sunway Blue Light, the processor is very different. So to facilitate deep learning applications, the first thing that we have to do is actually to build this deep learning software stack. So these are the things we have built so far. We have the Sunway gem to support highly efficient matrix operations, and then we have the Sunway DNN, which is kind of the counterpart to the CU DNN for GPUs. And based on Sunway DNN, we have also developed the Sunway Auto DNN, which is a kind of a tool that can automatically optimize the deep learning kernels for different kinds of problem dimensions. And above that, we have the Sunway Cafe to support kind of parallel deep learning training processes on this Sunway TaihuLight supercomputer. So some brief introduction about the second version, the Sunway DNN version 2.0. So as you can see, all these key elements that you would need to use for your deep learning applications are all now supported for the Sunway DNN version 2.0. And it has very good convolution efficiency. If you talk about the equivalent performance, we are actually providing 3.6 teraflops of convolution performance using this 260 core Sunway many-core processor. And also for the memory bandwidth utilization is somewhere around 80%. And as I said, based on the Sunway DNN, we have developed the tool into an automatic tuning framework for Sunway DNN. As you can see in the figure, for different kinds of framework, we can automatically do the tuning of these different kinds of parameters and trying to achieve a pretty good level of performance for all these different kind of dimensions that you would need to process in your specific problem. And for Sunway Cafe, the major part is trying to solve the communication issue. Now for the supercomputers, of course, we have our specific topology and we have our higher bandwidth communication the interface between these different computing nodes. So one of the key design issues is actually to let the software, let the MPI know about the topology. So we have done some reordering of the logic numbers according to the topology position so as to reduce the communication costs and to improve the communication efficiency as well as the scalability of the deep learning framework. So this is the benefits by doing so. As you can see, we can already scale the AnnexNet and ResNet to somewhere around 1,000 MPI processes. And as you can see for the communication performance here, we describe it as the all reduced bandwidth. We can improve it by over 10 times using the topology aware approach we have just talked about. So this is for deep learning. Now, I will give you another example about scaling K-means on Sunway TaihuLight. So for the previous efforts that try to do very large scale K-means on supercomputers, usually they're doing it by level 1 partition, that is to consider the different data samples, or combined 2-level decomposition, that is to consider both the data samples and the parameter k, that is how many clusters you want to classify these data items into. That is the number of centroids. And in our work, we are actually trying to identify another level of parallelism. So we're actually doing a 3-level decomposition approach. We are considering both the number of data items, the number of centroids, the parameter k, and also the dimension of the data. And by doing so, actually our work could support very large number of dimensions. That is for high dimension kind of data sets, which is pretty common in many different scientific applications. We can achieve pretty good performance. So here is some, you can see some experimental results for the cases of pretty large number of centroids, up to 2,000, and also a large number of dimensions. As you can see here, we are doing something around a dimension of around 200,000 dimensions. We can still handle it in an efficient way. And this is a comparison, a direct comparison between the 2-level decomposition and the 3-level decomposition methods. As you can see, the 3-level decomposition approach is obviously doing better when we scale up to a large number of nodes and also a large number of dimensions that we want to deal with. Okay, so that is the introduction about the different kinds of AI software, deep learning, and K-means on Sunway TaihuLight. So in the last part, I'm going to come back to the Earth system again and trying to show you some examples about how we could use these kinds of machine learning algorithms and trying to extract some more information from the satellite images and even to help the climate models to get better results. So yes, this is again the example of different kinds of activities we can do by analyzing the rich set of remote sensing data sets. The first example I'm going to talk about is the global land cover mapping we have mentioned, trying to produce a global land cover map that actually describes the classes of land use in different locations on the Earth. So this work actually starts in my department, I think 7 or 8 years ago. This is an effort led by Professor Gong in my department, and he has actually built the first 30-meter resolution global land cover maps, as you can see here. By using the traditional support vector machine on all these different Landsat sims, and at that time this work is actually done on Tsinghua's own supercomputer instead of Sunway TaihuLight. By using the Tsinghua supercomputer, we can actually finish the mapping of a global scale in 1 day. The accuracy was somewhere around 33.72%. So was not that exciting, but it's the first version of 30-meter global land cover map that people can use for various kinds of studies about the Earth. And collaborating with Professor Gong, we were trying to see if we could use the deep learning approaches into this problem. The first attempt was actually quite simple. We just tried to apply the stacked autoencoder method into the land cover mapping of the Africa region. And as you can see, a direct use of the method, it provides slightly better result, but not improved in a significant way. If you think about this issue, it's actually, so these are the Landsat images. It's a 30-meter resolution. So a square of 30 meter by 30 meter is described as 1 pixel in the image. So even for human beings, you look at the image, you can't really tell the differences between different land use types. So actually, in traditional methods, most of the information is collected from the spectrum information. By looking at the spectrum patterns, you can tell a lot of differences, like between the water and the soil. Of course, the spectrum signature would be quite different. So in order to improve the performance in a reasonable way, we are trying to combine the benefits of the traditional method and also the new deep learning methods. Now, the deep learning methods has proven its advantage in processing different kinds of images. So we were trying to combine the textual information that you can extract using the deep learning neural networks from the high resolution Google Earth images. And then we combine it with the spectrum patterns, the spectrum information that we extract from the Landsat image and combine them into one to make better predictions of the land cover map. And by doing so, we can actually improve the accuracy for the land cover map in China from 80%, from somewhere around 80% to 84%. And as you can see, that improvement is actually quite good for land cover mapping studies. So this is again comparison between the results. As you can see, the traditional methods, the random forest, the supported or the support vector machine, looking at the Landsat data, it can generate somewhere around 80% accuracy. Now, by directly applying the CNN method to the Landsat datasets, we can improve it to somewhere around 81%. Only by combining the high resolution Google Earth image with the spectrum pattern from the Landsat image, we can improve it by somewhere around 4%. And here is the results of the land cover mapping problem. As you can see, for some of the kinds, especially like for the improvers, that is the buildings that people built, you can see that the new method is recognizing those things in a much more efficient way. Okay, so and I think it's in the year of 2019, Professor Gong's group actually improved the global land cover map from 30 meter to 10 meter. And from last year, we have started to think about the problem, whether we can further improve from 10 meter to 3 meter. Now, the major problem for doing so is actually not in the method. It's actually more kind of in the data sets. Okay, we have collected labels for training processes for 30 meter resolution and for 10 meter resolution. But for 3 meter resolution to do a global study, we can't really afford the human power to do the labeling work. So we actually propose another approach. We're saying, why don't we just use the land cover results of the 10 meter land cover mapping as the labels? Now, of course, it's a noisy labels, right? The accuracy is somewhere around 80%, so many of the labels are not correct. So what we propose is that along the way that we train the models, we also update our labels. Okay, so as we have mentioned, by using the 10 meter land cover results as the first version of labels, we iteratively update the labels according to the classification results of the CN networks. So we do the uncertainty analysis, trying to distinguish the parts that are probably more accurate and the parts that have some doubts. And for the parts that have some doubts, we iteratively update the labels, trying to improve the accuracy. So by doing so, we can actually generate pretty good 3 meter land cover map for the region of China. So this is for the city of Changsha. So actually by doing so, we are minimizing the efforts for manual labeling of the results, and also we further improve the accuracy from somewhere around 80% to 85%. The second example I'm going to show here is detection of oil palm trees. So here are some different kinds of things we could do with oil palm trees. The first thing is mapping, right? From the high resolution satellite images, first we want to figure out which parts are actually the oil palm tree farms. And the second one is for those specific regions, we can try to detect the oil palm trees. Like we count the trees, how many trees we have in this region. And further, if we have even higher resolution UAV images, we can do finer classification. We can try to detect the growing status, whether it's a big tree, a small tree, a normal tree, or some tree that needs attention from the people, right? So we can do further stuff. So here, the first thing, of course, we still need to build up the data sets. So we have picked several regions in Malaysia, and we have made labels for those kinds of different oil palm trees. So the first method that we try to propose is a multi-level CNN network for detected oil palm trees. So actually use a two-stage CNN method. The first stage is a first CNN network that tried to, as we mentioned, to do the land cover classification, that is trying to locate those regions with oil palm trees. And the second stage, the second CNN network is trying to actually detect the trees, the oil palm trees, as we mentioned, to count the trees, how many trees we have in this region. And another thing that we try to do is we try to generalize our models, right? You know, Malaysia is a country that is very rich in oil palm tree plantations. So we have oil palm tree plantation in many different regions in Malaysia. If we want to really do a country-wise study, for example, we want to count the trees of all over the country, then we need a model that can be generalized, so that we have tried the DA methods, the domain adaptation methods, trying to reuse the model that we trained in one region with labeled data and trying to transfer the learning to a different target region that we don't have labels. And by minimizing the kind of a pattern difference among different regions, we can achieve sort of a more generalized model that we can use for many different target domains. So along this direction, we have also made some progress. So currently, by doing the DA efforts, we could improve the performance of the models in different target domains by somewhere around 10 to 15%. Okay, so these are the two examples I'd like to show you here today. And there are even more examples, especially for the city area where we have even finer resolution data sets. We can do even more things, right? Nowadays, the tools that people develop to extract the buildings, to extract the roads is already operating at a similar level of accuracy to the human. So these are really exciting stuff we could do to provide better methods for people to look at the image and trying to extract some more data. And as I mentioned, most importantly, we could use these higher resolution image processing information to provide help for the current climate models and trying to make better description of the climate change that is happening and trying to make better predictions into the future. So with that, I should end my talk today, and thank you for your attention.